Hello everyone, you're welcome to today's session. So we'll continue from where we left the last time. So remember, in the previous two videos I've done about random variables. I've done probability density functions and then cumulative distribution functions, right, and CDFs. So basically these are the two things we've done. But then how do these things fit into the general idea of random variables? So basically today's session will be considering uniform random variables. From then I will do exponential, and then from then I will do our normal distributions. So exponential distributions, normal distributions, and then basically we'll be done with all the slides. Okay, so what is a random variable? Basically we are considering like so you have a set of possibilities that will have a likely chance of occurring, right? So basically that's how it is. So it's just like you have some set of possibilities and everyone is equally likely to occur. So you can just take an example of rolling a dice, right? All your all the numbers, like the 1 to 6, they all have equal chances. But then in this case, we are considering not just discrete numbers, right? We are considering the whole range. So let's say if you had a range of say A to B, then everything in between that range is equally likely, whether it's a whole number or not, right? So basically, that's the whole idea of a random variable, right? Sorry, a uniform random variable. And let me give an example before we continue. So, for instance, you want to find so you have a range of ages, right? So you have a lot of children, like let's say 1 million children, who's okay. So who are between 1 to 10? 10 what? Let me see. Okay, let's say who are between 0 to 10 years, at least, right? Okay, let me say 1. That would not make sense. So let's say 1 to 10 years, right? And then you want to find a child who is exactly 5.6732 years old, something like this. It's possible because if you calculate the years and take the days and all of that. So let's say you want to find someone who has exactly these years. You will find that it is really like your probability is almost zero. Like it's very unlikely. But then if you want to find, or even five, because most of the times people are not exactly the age, right? Someone, maybe you can say you are 5 years old, but really you are 5 point something years old. That's if you're considering all other days. So you find that this is really unlikely to happen. But then in uniform random variables, what we are doing is that we are not considering the location, we are considering a range, right? So that's what we are talking about. So you have some f of x here, which is always some particular value, right? Some particular value because everyone is equally likely. And then you have, let's say, your 1 here and then your 10 here, right? So basically, all the children you are looking for are in this range. And then you want to find someone who is a particular specific age. Your probability of getting the person might just be zero because they are infinite. So you have 1.111, 1 point this to even 9.999, right? So all of those possibilities are there. And then you so your best chance is to find a range. So for instance, if you want children who are from say 4 years to 5 years, right? So you find that you would get more people here than you can possibly say I want a child who is exactly on one of the lines. So that's why in uniform random variables we use intervals, right? So the probability really depends on the interval, not really where it is, because literally everyone has the same height. Okay, so I hope this long explanation helps, and then we get to the main thing. Okay, so the probability distribution function or probability density function, sorry. So the probability density function of these random variables. So since we know that, let me take another graph. Okay. So some a and b here, we have f of x. Since you know that they all have the same height, right? And then once they all have the same height, what's like so the major thing you can do here, right? The probability distribution function can be defined as so the integral, bad integral, b minus a, sorry for my integral, okay, for all the values from x to b, right? And then for anything else that is outside that range, it's just zero. So you just say otherwise. So this is how the probability distribution density function is defined the for a uniform distribution. Okay. So this is how it will be expressed in the form of a graph. Okay. Sorry, the wind. Okay. And as we know about probability distribution functions, they all have similar, should I say, properties as we discussed previously. So we know that the area of this, right, the area of this box here is exactly 1, because we're dealing with probabilities. That's the only way to make sense. Okay. And then you also have a cumulative density function or a cumulative distribution function. Okay, I actually sometimes say these things interchangeably, but then I think in my previous video I defined clearly what the difference is between those two are, so you can check that out if it's a little bit confusing. Okay, and then for this one is defined as, so basically, remember in the previous video when we are defining your probability distribution function, so it's 0 for anything less than, so less than or equal to the lowest, and then for anything greater than or equal to the biggest, and then everything here is defined as that, so from whatever point you are dealing with minus the first, all divided by the last point minus the first again, for a less than x less than b, right? So these things are just principle, so and you can also estimate them, but then let's not go so much into that. So let's just get to the main thing. So over here, what we'll be doing basically, we'll be finding some expectations. So we'll be finding expectations of some x, the mean, right? So the expectation is the same as the mean. You can find some variance, you can find some standard deviation. So these are the things they can ask you to find in a critical, like in a main question. Uh, yeah, most likely no one is going to ask you to explain those terms. But then it's good you know what they mean, right? And then for this, so for probability density function, the graph looks like this. And for this, as you can imagine, it will have a form of something like this, and then it will rise with um, some constant gradient, and then till it levels at 1. So this side will be 1 and this side will be 0. So basically, this is how the graph will look like. Okay. Okay, so let's do the first thing we have to do here. So first of all, let's say you want to find your expectation of x. So let's find expectation of x, and then from the previous video we've already established that the expectation of x is f of x dx, right? So x times f of x dx. So how do we go about with this? Now we know that our f of x, like we define in the PDF, is 1 over b minus a. Okay, so we can decide to input this. So now we won't be dealing with negative infinity and positive infinity. So basically we'll be dealing with two measure points a and b, right? All times that. So x dot that, so that's b minus a. You should also understand that these b minus a are not constants. They are actually some x's. Okay, they're actually some x's. So how do you solve something like this, right? So basically integration, right? So you just integrate it. This will be affected, and then you'd have your x squared on 2, right? Then you multiply by your 1 on b minus a, and then from your b to your a, right? Right, sorry, the upper limit is b to a. Okay, so basically this is how it will be expressed, and then from here you can decide to simplify this, Then you'd have your b squared on 2 multiply 1 on b minus a. Then you subtract your a squared on 2 multiply 1 on b minus a. Then you find that you can factorize out your b minus a. Actually, you can factorize out 2 times b minus a. So 2 times b minus a, you can factorize this out. Then you end up having b squared minus a squared inside. Then you find that this is practically a difference of squares. So you can have, so you can expand this one to have your b plus a and your b minus a. So now with this, you can just take one of these things off. Then you have b plus a on 2, which will be defined as your expectation of x. Okay, so this will be the expectation of x. So in other words, it will be the mean. Okay, and now the next thing is to find your, okay, so that's all, basically that's all. And then if you want to find your variance, um, the last time we defined variance as something like this, right? Or you can also define it as expectation of x squared minus expectation of x squared, or you can just change this one with u, it's the same thing. So this is how you defined your variance. Now to calculate our variance, we need to estimate this function because we've already found this to be that. So for a uniform distribution, if you know this general formula, you don't have to go around deriving it all the way again when you're actually having a question. So you can just go straight ahead and use it. So for this one, let's just get to it and see how it look like. So you would have integral of x squared multiplying 1 on b minus a dx. So from a to b. When you integrate this, you have s cubed on 3, right? And then you multiply by your 1 on b minus a. And then you take your limit b to a. Okay. Now with this one, we can further simplify it to get b cubed on 3 minus dot 1 on b minus a minus a cubed on 3 dot 1 on b minus a. Okay, I should have written this one. Okay, but anyway, so we'll do the same thing with it. So we have 1 on 3 times b minus a multiplying b cubed minus a cubed. Okay, so now at this point you find that you have something looking like this and you have to simplify this down. So with this one, you have to draw you have to remember some information from how to expand these things, right? So basically expanding b cubed minus a cubed, that would give you b minus a, then you multiply b squared plus your ab, and then plus your a squared. Okay, if you want to prove this, you can actually expand. So if you expand, you find that um, the middle terms will cancel out. So basically you end up having this one times this minus this one times this. Right, so basically this is how it look like. And when you fit that back into your formula, you have your expectation of your x squared to be this one will cancel out with what's already down there. So you have b squared plus ab plus a squared all on your 3, right? So this will be your expectation of x squared. Now you want to find your variance, then you can conclude that your variance is b squared plus ab plus a squared all on 3 minus b plus a on 2, right? And this one, if you do the algebra, yeah, you end up with something like b squared minus 2ab, and then I think uh, some a squared, is that right? Okay, so basically if you have some time, you can sit down and solve this, and then you have b minus a, right? And that basically be b minus a squared. Okay, all on 12, and this would be your variance. Okay, So we've settled on what your just to recap, your expectation of x is always that's the mean, and which is always equal to integral of x f of x dx. So you find that throughout what we've been doing, it doesn't change, it's just the same thing. And even you realize that in exponential functions and then normal distribution, it's just the same thing. It just we just do simplified forms. Then you find your so for this case, it will be b plus a on 2, and then you find that your variance will be equal to integral of x squared f of x dx minus your mean squared, and in this case we have b minus a all squared on 12. So basically we are set. Okay, so now that we've settled on this, right, now that we've settled on these two, and then just in case you want to find your standard deviation, you can just take your square root of variance, and then you have that. Okay, so now that we've settled on this, let's try solving an example, and basically we'll just take the examples from the slides because mostly that's what he repeats. Okay, so if you check example 4.9, let me see if I can get for you to see. It's quite okay. So this one, right? So let's just define our terms. Our range can be defined as 0, 20. I'm just taking the most important things. Okay, so I think that's just the even. So what's the probability that a measurement taken is 5 to 10? Good. So basically, I think we've had everything we need. So now this is the question they're asking you, right? So this is your A and this is your B. Now this how graphically this how it will look like. So you know that this will be constant, and then this constant thing is what? So basically, let me just leave that there before we just continue, and then we have so we have from 0 here, right? So let's say from 0 to just want it to be at the origin from 0 to 20. Okay, so like I explained earlier, we are trying to find for some range which will make more sense. So if you are trying to find for say 4.9 or maybe 5.2 milliamps, you'll probably just get 0. But if you are dealing with a range like this, you are expected to get something, right? So basically this is what we are going to be working for. So the first thing is what are you supposed to find? So they want you to calculate so what's the probability that a measurement of a current is between 5 to 10 milliamps? Okay, so you are trying to find the probability within that range. And how do you define your probability density function? So basically you're looking for your probability density, then that will be from your A to your B, right? So where your A is your 5 to your B 10 of f of x dx. Good. Now this is f of x. What do you get for here? So just don't confuse yourself with these two things. So with this f of x, you are dealing with the general range for everything, right? So from 0 to 20, and then you remember we define this as 1 on b minus a. Now this b is the maximum b, this a is the minimum a. So that would be 1 on 20 minus 0, which gives us 20. 1 on 20, you can keep it as 1 on 20, that's fine. So this is our f of x, okay? So basically, if we are to solve for the probability density function here for the uniform distribution, then we can just say 5, 10 on 1 on 20 dx. When we are done, we'll go through the, should I say, the more direct method. Okay. So this one, you can just do your normal integration. Then you find that you end up at 1 on 20 times x. Where did the square come from? And then 10 to 5. Okay. It will look like this. Then you do your subtraction. So 1 on 20 times 10 minus 1 on 20 times 5. Then you realize that you end up with 1 on 20 times 10 minus this. That will basically give you 5. So this will be your answer. I think if you simplify this, then what should you be getting? You should be getting 0. 0.25. Okay, so basically this will be 0.25, and that will be your probability density function. Now from here they can ask you to find your mean. I think the question in the slide, I think they added something on it. So if you have to find your, sorry, the wind. Okay, so you have to find your e of x. So there are two ways to do this, right? You can go with the general method, like we did the last time. So you can do your integral x f of x dx from to the limit you're dealing with. But basically, we know that this is a uniform random variable. So we'll use the methods we found. So over here we found that expectation of s is b plus a on 2. So b plus a on 2, where is our, so our largest number is 20, smallest is 10. So b plus a on 2, that will give us 20 on 2. So that will be 10 milliamps. Okay, I hope this is clear. And then for our variance will, it will also be quite direct. We have b minus a squared on 12. This is what we found. Okay, now b minus a will still be 20, so 20 minus that, so will still be 20, all squared. Then that will be 20 squared on 12. You have 412, and then you should be expecting something like 33.3. Okay, so 33.3, this should be our answer. You can add your units, that's milliamp squared. Okay, now with this one, if you want to find your standard deviation, then you can decide to take square root of 33.3, then you should be getting 5.77. Okay, so basically this is how you go ahead um, solving questions from random variables, uniform random variables, right? So basically, let's just wrap. I don't think there is not anything else to this, so I'll just move on to the next one. So basically, if you are asked to find your expectation in a, so, or the mean in this one in a uniform distribution, then you can have your b plus a on 2. Then if you are asked to find your variance, you can just do b minus a squared on 12. Okay, but then you have to take note that this b minus a, these are the extremes, they are not. So if they give you something like this, ask you to find the probability, they are asking for the probability density function. So that's what they're actually asking for. Okay, and then after that, so once you ask for these things, then you can go through this method. I hope this was helpful. And then if you have any comments or questions, you can just put in the comment section. I'll check it out. And then I realized that in I think two of the past videos I made two mistakes, as in the calculation, not the concept. So sometimes when you see some of these things, just draw my attention. But I'll try to be keen on mistakes as we move on. Okay. Thank you for watching, and all the best in the exam.